or whether it looks like what we might call the organized complexity that is more characteristic of a language. Carl Sagan, in his science fiction novel Contact, investigates this particular question again. It would seem then that perhaps 100 or 200 or 1,000 pieces of information, digits of information, bytes of information, would be enough to tell whether you're looking at something random or whether you're looking at something that is real, intelligent, if you like, or an intelligent designer lies behind it. Interestingly, the most complicated thing we know of in our universe is life. And the information content of even a simple E. coli bacteria, you know, it's a prokaryotic cell, not a complicated one, etc. Sagan says in his article Life in Encyclopedia Britannica, the information content is equivalent to 10 to the 12th power bits, or about 100 million pages in the Encyclopedia Britannica. And it's not just random stuff, it's making a working machine. That sounds to me like we are getting a message from E. coli that it was designed, and that a person who claims that anything else is happening is under a certain obligation to show how such a thing could have designed itself. And not just by waving hands, but at least by some kind of computer simulation that you can get from the kind of information content in simple molecules up to the kind of information content of 100 million pages in Encyclopedia Britannica, by random processes, even though constrained by natural laws.
What have been the prevailing scientific theories of the origin of the universe?
In this century, as we've begun to learn a little bit more about galaxies moving apart from one another, and we've begun to learn a little bit more about the energy sources in stars and how stars produce their energy and that sort of thing, we've had a sifting down, if you like, of available cosmological models. A century ago, a century and a half ago, an atheist might very well have felt that the universe has always been here and stars perhaps have always burned, and yeah, we don't know how a star could keep going infinitely, but we don't know how stars keep going anyway, so no big deal. But with the discoveries of the nuclear processes, with the discovery of the expansion of the universe by Hubble, and actually a little earlier by his predecessor, it's become apparent that you're in an expanding universe that is running down in the sense that it's using up the hydrogen fuel and such available. The upshot of that was, by the end of World War II, two basic kind of models had arisen in scientific circles for cosmology. One of them was a model that the universe came into existence in some sense at a finite time in the past and has been expanding from that, a Big Bang model. And perhaps we should say a little something later about varieties under that. And the other model was, no, the universe has always existed, but matter is popping into existence continually at a finite rate, what's called the steady state theory of the universe. And those have been kind of the two big models from the late 1940s up until the mid-60s and perhaps even into the early 70s. The story of how they seem changed is a rather interesting one.
How did the shift from a steady state model of the universe to the Big Bang model take place?
The story of the shift from a competition between steady-state cosmology and Big Bang cosmology is rather interesting. In the late 40s and early 50s, when the Big Bang, when the steady state was first proposed by Herman Bondi and Fred Hoyle and Thomas Gold, they really claimed their argument, their position was philosophically and scientifically much superior to the Big Bang, because the Big Bang proposed a cosmological principles. Things look the same in all directions over large areas of the universe. But they proposed the perfect cosmological principle, that things not only look the same in all directions, but they look the same at all times in the history of the universe. That in their model of the universe always had about the same density over large volumes. It always had a certain number of dying stars and a certain number of new stars and a certain number of new galaxies and old galaxies and that sort of thing. And they said, you know, this is really the scientific feature of methodological atheism or methodological naturalism spread out, you know, carried to full degree. And I think a number of people bought into that. However, a problem developed fairly early on, and that is, as they began to try and look further and further into the universe, researchers were trying to find out whether we lived in a universe that looked like it was getting thinner, less dense now than had been earlier, or whether the density looked like it stayed the same at all times in history, because the Big Bang predicted a hot, dense universe that was becoming thinner and cooler as it went on, whereas the steady state predicted a universe that was staying the same density and temperature on large volumes everywhere. Well, the first thing they did was they began to try and make counts of galaxies per unit volume, and it looked like there were more galaxies per unit volume at great distances than there are nearby, and that was assumed then to be earlier in its history than currently, and that favored a Big Bang type universe. Steady state proponents could basically say, well, there may be all sorts of features regarding the aging of galaxies, or even regarding the absorption of starlight and things of that sort that may affect that, so it's hard to really be sure about that. But then quasars were discovered early in the 60s. Quasars, we're not sure what they are, although the general guess now is they are very unusual centers of early types of galaxies. These things can be seen at enormous distances. Some of these quasars appear to be visible as much as perhaps 10 billion light years away. They hadn't seen any that far away in the early 60s, but they were certainly looking at what we might call cosmological distances, distances that the light traveling would be traveling a substantial fraction of the history of the universe if it were a Big Bang universe, and a substantial fraction of the lifetime of stars even in a steady state universe. And what they began to see immediately was there were lots more quasars way back in the past than there are now, as best you can tell. Realize in cosmology you can't tell the difference between distance and time because we can't wait around billions of years. So distant objects you're seeing from way back in the past and such. So that's began to become apparent. And that began to put a stress on the steady state theories of the universe. And perhaps the last nail in the coffin or something of that sort was this discovery by Penzias and Wilson that all the sky in the radio frequency wavelengths was glowing at night. And the glow was the same in all directions, and therefore was a cosmological glow, not a glow from our galaxy or a glow from our solar system or a glow from something else. It was something that was the same in all directions. And that, of course, has panned out very nicely in recent years now with the COBE satellites and such, seeing a very, very good fit of this black body radiation, of this cosmic radiation, as fitting a temperature of just under 3 degrees absolute. What that showed, I think, is that the models of the Big Bang, which had already predicted that there would have been some point after the Big Bang a time when the universe became transparent, and they estimated what the temperature would be at some 3,000 degrees, and that by now that would have dropped down order of 3 something degrees absolute. And here it was. A prediction made by Gamow, one of the Big Bang men, was panned out in the research. And so that really was kind of the last straw, so to speak. Fred Hoyle held on to his steady state theory for a few more years. He seems to have gone out of it now, but that really was the end of that. We have a universe which had some kind of a beginning at the Big Bang.
Could you discuss some of the submodels of the Big Bang?
In the history of the Big Bang theory, there have been lots of varieties proposed, and I'm not going to get into cold matter and that sort of thing. But one way of characterizing the models was the original model proposed by Georges Lemaitre in the late 20s, and would be obviously modified as we come up the line, is that the universe really began with the Big Bang. Would be a creation model of a thing, and before that there was no universe. Okay. George Gamow, a Russian cosmologist who fled to this country in the 30s, felt that that wasn't very satisfactory. He wanted a universe that had always been in some sense, so he proposed that this Big Bang was actually a big bounce, and that for all eternity before that the universe had been getting its act together and collapsing. It bounced at the Big Bang, and now it's been expanding since. The universe would have been a rather uninteresting sort of thing until the bounce, but it's been quite interesting since then, but it will run down eventually and be quite uninteresting forever after all the stars poop out. So that was basically Gamow's version. And the advantage of that for many people was that avoided a creation, avoided a creator, left us with a self-contained universe, and many people found that very satisfying to them. Third model I'm not sure who the original proposer of it was. The earliest version I've run across was by a fellow named Heir.BEWARE, and that's an oscillating universe. And that is, yes, the Big Bang was a big bounce, but it was only just the last big bounce. And perhaps every 100 billion years, the universe bounces. It expands then for, say, 50 billion years, gradually runs out of steam, and falls back on itself. But instead of, but then when it gets compacted enough together, it bounces and expands again. And that has actually been the variety of the Big Bang that's been most widely popularized, that Asimov would typically present, or that Sagan in his Cosmos series typically presents, etc. And the advantage of that was felt to be no God, and we're not in that unusual time period in the universe. Every 100 billion years you've got a time period when you've got the stars running down, you've got life flourishing on certain kinds of planets and such. And so that was really the story, the kind of standard, if you like, blind watchmaker story expanded to cosmology.
What are some of the problems with the oscillating model of the Big Bang?
When we analyze these three different versions of the Big Bang from the perspective of how they handle the data, we find something rather interesting. And that is that two of the models require the universe collapsing to bounce and go back out again. And the question is, would that happen? Well, not with the four known force laws that we have today would that happen. You have to postulate some other kind of force. The force laws that we know about today, gravity, although it's the weakest force under normal circumstances, if you get matter close enough together, dense enough together, it overcomes all the other forces, and gravity is an attractive force only. It's not a repulsive force. And so as a universe collapses and gets more and more and more and more dense, it doesn't bounce. The universe pulls itself into a black hole. You know, goes, and it goes into the black hole. I'm not sure what the sound effects are, but that's basically what happens. So they had to propose there's some kind of force that would somehow stop that from collapsing. Robert Jastrow pointed out, though, that if you have any kind of a force that you imagine that's a repulsive force that's going to push the universe apart when it gets crowded enough together, you run into a catch-22 situation. And that is, this force is going to act like an energy, and that energy will have an equivalent mass through Einstein's equals mc squared, but that will add to the actual rest mass of the universe. And that additional mass added to the rest mass will make the gravitational force stronger than this force you postulated, and it will pull everything into a black hole. And it didn't look like get around that. Stephen Hawking came along a few years later, and he showed that even if you ignored that sort of thing and imagined a universe that could bounce some way, that a universe that had been through a cycle and had bounced like that would have much more disorder in it than our universe does. The entropy would be much higher than ours is. And so it appears that he drove the last nail into the coffin of bouncing universe Big Bangs, leaving you really with a no-bounce Big Bang, a universe that began in some sense at the Big Bang.
Would you comment on Stephen Hawking's Brief History of Time?
Stephen Hawking's book, A Brief History of Time, is a very clever book. And it's a very nice introduction to modern cosmology in all but its last chapter. A nice tour of the science, a nice tour of the theory and that sort of thing. Very, very nice. In the last chapter, something that seems to me irrational happens, and that is Hawking is scrambling to avoid the natural consequence of the model he has, which is that the universe had a beginning. What he tries to do is say, let's imagine that time is not just a real variable, but it is a variable that has an imaginary part to it as well as a real part to it. So it's a complex variable. And then we can take this expansion of the universe from this Big Bang and coming out, and he's going to have it fall back on itself, actually, though we've got some problems with the evidence for that. But now we can rotate that figure around an axis, around this time axis, and we get, instead of a little loop sticking up like this, we get kind of a football-shaped thing, okay? And that avoids the singularity back here. What was originally a singularity now just becomes that end of the blimp, or that end of the football, if you like. And we've got this nice universe that kind of starts over here and goes out and ends over here, if you like. But that's all there is. There's no time back here before this, and there's no time after that. Therefore, we don't need to explain where it came from and such. But in fact, what he's really done is he's made a universe that has popped into existence without a cause, and is going to pop out of existence without a cause at the other end, no matter how you wave your hands. And in a sense, he violates, I think, not only one of the most basic thing we might call laws of science, causation, getting a whole universe out of nothing, but he violates what is, I think, probably the most basic law of common sense. One would at least want some very good evidence before one abandons a thing like that. Others have preferred to do something like that, but have that universe embedded in a bigger universe. Some would like to make that a universe of nearly infinite temperature and density, and we're a very cool bubble in it, where they would get the evidence for that as opposed to some kind of a mathematical model. I don't know. The universe would have to be very insulated and such. I think we're in better grounds for saying, yes, there is something infinite beyond our universe, but that infinite being is personal, and he is the author of Scripture and such, on the basis of real evidence that Christianity is true.
What is your take on the anthropic principle?
The term anthropic principle has been used as an attempt to explain the fact that this universe is marvelously hospitable to life, and our Earth is marvelously hospitable to life in particular, and to even all the way up to humans and such. And they don't want to say it was designed that way, right? If you say it was designed that way, you pretty quickly get into some kind of a theistic worldview. And the anthropic principle in general is a view that's attempting to short-circuit the evidence from design to a designer by saying, if you've got enough things that happened randomly, some of them are going to look designed. If you've got 50 trillion chipped rocks, you might be able to find one of them that looks a little bit like an arrowhead. You only got one rock that you pick up and looks like an arrowhead, and looks very like an arrowhead. It's designed. But if you've got 50 trillion rocks you're looking at, and you can see some of them that look a little bit like a hockey puck, and other ones that look a little bit like a axe and that sort of thing, and most of them don't look much like it, you say, no big deal. This one is probably just, you know, I've selected it out, okay. Well, they would say, out of all this huge, almost infinite number of universes, we're in the one that has been selected out by having intelligent observers inside it. If you've got enough universes, you're bound to get an intelligent universe inside one of them, and we're it. And of course, we can't be inside a universe that doesn't have intelligent observers, because we're intelligent observers, okay? So of course it's going to look designed. That's what we're doing. As I pointed out earlier, that seems to me to be true, except we don't know there is all those universes out there. We've only got the evidence for this universe. And in a design, in a model in which you have design, a designer, you would naturally expect to have evidence of design in the product, okay? So a theistic worldview naturally expects a designed universe. An atheistic worldview can only get a designed universe, apparently designed universe, when we're getting away from mutation and natural selection, although that's got problems, by having an almost infinite array of universes, either in time. We're the 585 trillionth universe since so many quadrillion years ago or something like that, or by having a whole bunch of them at the same time, or something of that sort. What I would say is, when we're picking models, even worldviews, a worldview in which the phenomena that we see is a natural result is a better worldview than one in which it's the unnatural result. And using natural in the sense of what you'd expect, as opposed to can't have any supernatural, a theistic worldview comes out looking very, very good for explaining the kind of universe we've got.
What lines of evidence are there for an intelligent design of the universe?
One line of evidence relates to the balance between the four basic forces that we know of in the universe. The very weak gravitational force, the so-called weak nuclear interaction, the electromagnetic force, and the strong nuclear interaction. The balance of these is really quite necessary to have a universe that would last long enough, as ours has, to have life upon it, to form stars and galaxies and planets and that sort of thing. And yet a very, very fine balance between the expansion rate of the universe and the tendency towards gravitational collapse is necessary for a universe to last long enough for that to happen. Some have suggested that shortly after the Big Bang, that the relationship between expansion speed and the force of gravity would have to be tuned to 1 part in 10 to the 60th in order for the universe to not expand so fast that you would never form stars, galaxies, and planets. Or, on the other hand, if the speed is not fast enough, that the thing would collapse back on itself and never form those things.
Could you give another example of intelligent design in the universe?
Another example would be the balance between the positive and negative charge in the electromagnetic force. Electromagnetic force is like gravity, a very long-range interaction. They both decrease as the square of the distance. And yet electromagnetic force is so much more powerful than gravity that if the electromagnetic force were not balanced, a almost exactly equal number of positive and negative charges, it would swamp out gravity and would give us a very drastically different universe than we've got. You would not have a universe of hot stars with cool planets rotating around them such as we've got. Since there's a difference in about 10 to the 40th power between the strength of gravity and the strength of the electromagnetic force, that means that the number of electrons and protons or equivalent carriers of positive and negative charge have to be equal to within about 1 part in 10 to the 40th.
Are there physical parameters in our solar system that require fine-tuning?
It appears that only a sun of around the size of our sun will last long enough to have the history of life that we see on our Earth, that will produce a right balance of what should we say, the spectra of radiation that life operates where. If your spectra is too much short wavelength, you break up the complicated molecules. And in fact, our Earth even protects that by having ozone layer to knock out the ultraviolet side of it. If the spectrum is too low, that the star is too cool, then you really do not get the high enough frequencies to make photosynthesis work, for instance. So the class of our star, a G2, is rather important in having a situation that we want here on the Earth to be able to allow life. The distance of our planet from the sun is rather important. You might think, well, you could have a bigger star and get further away from it, or a smaller star and get closer to it. But your bigger star further away, you have a short lifetime for the star. So that messes you up. Your smaller star, where you've got to move in closer, you're great. You got a nice long lifetime. You begin to have some troubles with having too much infrared and not enough of the visible. But a big problem you've got is as you move in closer, the tidal effects go up. You begin to get a longer day-night on the planet, therefore a bigger swing from hot during the day to cold at night, and then you begin to run very severe tensions on being able to have living things handle, say, 100 or 200 degree temperature change from day to night, and that, of course, is again quite drastic for living things.
How finely tuned must the distance to the sun be in order to prevent either a greenhouse effect or runaway glaciation?
A third feature related again, we think, to the distance of the Earth from the sun is the question of the incoming radiation to the sun, and that of course heats the Earth up, and then the Earth will move to a, what shall we say, to a temperature that is equal amount of infrared going out and the sun light coming in. That's influenced very substantially by the greenhouse effect. The amount of carbon dioxide and other greenhouse gases in our atmosphere are such that it raises the temperature of the planet perhaps 20 degrees centigrade above what it would be if you didn't have that kind of effect working. It appears now that if our Earth were a little bit further away, that even with our greenhouse effects, the temperature early on would have dropped enough that we would get what we call a runaway glaciation effect. That is, you begin to have large snowfalls during the winter, The snowfalls produce white snow, which reflects sunlight very nicely, and so then you get larger and larger areas until you have a ice-covered planet, rather like some of the moons of Jupiter and Saturn, which have that kind of a coverage. On the other hand, if you move it in just a little bit, you then have a situation in which the extra heat from the sun evaporates more water and begins to drive carbon dioxide out of the limestone rock, and you begin to get a big greenhouse gas, greenhouse atmosphere like you've got on Venus, and you have a runaway greenhouse effect in the other direction. And Venus is a nice example of that. A planet whose temperature, perhaps, if it had an atmosphere like Earth's, would be maybe 200 or so, but with the atmosphere it's got, it's about 900 temperature. So again, a balance there. The balance has been suggested by one researcher as if you were about 1% closer in, you would have had a runaway greenhouse effect, and a few percent further out, you would have had a runaway glaciation taking place in antiquity.
How finely tuned must the components of our atmosphere be in order to sustain life?
Another striking feature, which we might say looks like design, or at least looks like a very unusual feature of our planet Earth, is the way its atmosphere functions. If we had much more atmospheric pressure, we would have a runaway greenhouse effect again. If we had much less, we would be in bad shape for living things to be able to process the oxygen, certainly bad shape for birds to fly and that sort of thing. But even more striking is the balance of oxygen in our atmosphere versus the more inert gases, nitrogen particularly. Our atmosphere has about 21% oxygen, and almost all the rest of it is nitrogen, and then there's varying amounts of carbon dioxide and water vapor and such. If you raise the amount of oxygen in our atmosphere by 1%, other things being equal, you increase the number of spontaneous forest fires by 79%. So if you go up just about 4%, you wind up with no vegetation surviving on Earth at the levels of moisture we have. That is, the stuff all burns up in one way or another. On the other hand, if you go down just a few percent, you don't have enough oxygen in the atmosphere for animals to function. And so we're in a very narrow window in which both animals and plants can function in our planet. And of course, if animals can function but plants can't, as soon as you have eaten up the other animals, you're in bad shape anyway, and the bottom of the food chain has no support, which is needed from the plants. And I guess the plants could get along all right without the animals, except for problems of pollination and such. So there's some rather striking features there of design, it seems to me.
Water is obviously crucial for life. Could you describe some of its critical properties?
Yeah, water is a very striking feature of our planet Earth. Our planet Earth actually doesn't have much water, but it's all in a very thin onion skin on the surface. You go down very far, you don't have much. You go up very far, you don't have much. It's all right here, where you'd have to say where we need it, and not just us humans, but living things as well. And yet, of course, our Earth has got lots of water compared to Venus inward from us, where it's not there. It may be somewhat dispersed in the atmosphere or locked up in the geology, we'll call it. It's not geology, but the rocks of the planet. And likewise, out on Mars, we really do not have much free water. A little bit in the ice caps, but very, very small compared to what we've got. So the amount of water is really very, very favorable on Earth for living things. And I don't think it'd be fair just to say life as we know it, although you could certainly say something like that, because as far as we know, at least when we're talking chemical life, we're probably stuck with carbon-based life, because only carbon can make a wide range of different complex molecules that we've got. And the solvent you need, the really good solvent, is water. Ammonia can do a little bit of solventing at much lower temperatures where it's liquid, but it's nowhere near as good a candidate. Water itself has some very striking properties. It's a rather strange bent molecule, means that one end of the molecule, or actually the two wings of the molecule, have one charge, and the point of the molecule where the oxygen is has got another charge. And that allows it to be a good solvent, pulls other molecules apart with the electromagnetic effects there. It also means that when water freezes, the angle between these two bonds is such that it tends to freeze into a more open crystal structure than even the structure it has as a liquid. Water is one of the very, very few molecules that on freezing becomes less dense than it was when it was liquid. That has two rather important points in our biosphere. One of them is that when water freezes, it doesn't sink to the bottom of the lake or the river, it rises to the top, forms an insulating layer, and keeps then, in many, many situations, the river or lake or ocean from freezing all the way bottom to top, and preserves life underneath. Secondly, water in expanding on freezing runs down into cracks, breaks up rock, makes soil, etc. It's one of the important features in production of soil, along with earthworms and decaying vegetation and things of that sort. So some very striking features there as well.
How do those who do not believe in a designer explain the fine-tuning of the cosmos?
Those who believe there really is no design in the universe, that design is either in biology a result of mutation and natural selection, or in non-biological things, there they would say it's a fluke of observation. And it's this kind of a fluke. If these things didn't all fit together, if the basic forces weren't the way they were, if the size of our sun and our distance and the size of the planet and the oxygen on it wasn't the way it was, then there wouldn't be any observers. And so if you've got observers, then these things have to work together. That's true. A rather surprising thing about it, though, is that we're talking about some very knife-edge balances. 20 years ago, 30 years ago, in science fiction writers, they tended to think that you could have silicon-based life, and that you could have life on Jupiter, and that you could have life around big hot stars and life around little cool stars, etc. But that's beginning to look like, at least as far as we're talking about chemical life, that that's really not possible. So I think there's some real question whether the explanation that, well, if things weren't this way, we wouldn't be here. We're here, therefore they got to be that way. So what's the problem? Well, that's not really a scientific causal explanation. You know, if my mother and father hadn't met, I wouldn't be here either. But that doesn't say anything about how they met, nor whether it was likely or not, nor whether it's something we should be surprised about. And I think the knife-edge feature of it suggests we should be surprised. A biblical model, you might say, or a Christian model, a model from a Christian worldview is, we should not be surprised that we live in a universe with great evidence of design, because in our model there's a designer out there. Whereas in a worldview that there is no mind behind the universe, that we live in a blind watchmaker universe, the basic picture there we would get is, wow, why are all these things knife-edged like they are? Isn't it a lucky fluke that we are in this kind of universe we are? There must be trillions of universes out there, and we're just one of them. There's no evidence for trillions of universes. Of course, somebody might say, well, hey, we're just postulating a nearly infinite number of universes, but you're postulating an infinite God. Why isn't it better to postulate an infinite number of universes than an infinite God? And my answer would be, the infinite God has revealed himself, and we have good evidence in the sort of things we would call Christian evidences that there is such a God. Fulfilled prediction, changed lives, those sort of things. The historicity of the events surrounding Sinai and the giving of the law, of the events surrounding the ministry of Jesus and the resurrection, to me are very strong indicators that we're not just talking a hypothetical question of which model might explain some scientific evidence, but also evidence that we've had a communication from the God who exists.
What are the primary views of biological origins?
The primary views of origins that I'm familiar with anyway would be one, that we live in a blind watchmaker universe, a universe in which there's no mind behind the universe, and therefore all the diversity that we see in living things has arisen naturally. There's no guidance to it. It's purely a blind process. And that's often called atheistic evolution, or Philip Johnson prefers the blind watchmaker evolution, something like that, rather than just using a generic term, evolution. A second view held by many, many people today is that it's making a working machine. That sounds to me like we are getting a message from E. coli that it was designed, and that a person who claims that anything else is happening is under a certain obligation to show how such a thing could have designed itself. And not just by waving hands, but at least by some kind of computer simulation that you can get from the kind of information content in simple molecules up to the kind of information content of 100 million pages in Encyclopedia Britannica by random processes, even though constrained by natural laws.
What have been the prevailing scientific theories of the origin of the universe?
In this century, as we've begun to learn a little bit more about galaxies moving apart from one another, and we've begun to learn a little bit more about the energy sources in stars and how stars produce their energy and that sort of thing, we've had a sifting down, if you like, but matter is popping into existence continually at a finite rate, what's called the steady state theory of the universe. And those have been kind of the two big models from the late 1940s up until the mid-60s and perhaps even into the early 70s. The story of how they scene changed is a rather interesting one.
How did the shift from a steady state model of the universe to the Big Bang model take place?
The story of the shift from a competition between steady-state cosmology and Big Bang cosmology is rather interesting. In the late 40s and early 50s, when the Big Bang, when the steady state was first proposed by Herman Bondi and Fred Hoyle and Thomas Gold, they really claimed their argument, their position was philosophically and scientifically much superior to the Big Bang, because the Big Bang proposed a cosmological principles. Things look the same in all directions over large areas of the universe. But they propose, or whether it looks like what we might call the organized complexity that is more characteristic of a language. Carl Sagan, in his science fiction novel Contact, investigates this particular question again. It would seem then that perhaps 100 or 200 or 1,000 pieces of information, digits of information, bytes of information, would be enough to tell whether you're looking at something random or whether you're looking at something that is real, intelligent, if you like, or an intelligent designer lies behind it. Interestingly, the most complicated thing we know of in our universe is life. And the information content of even a simple E. coli bacteria, you know, it's a prokaryotic cell, not a complicated one, etc. Sagan says in his article Life in Encyclopedia Britannica, the information content is equivalent to 10 to the 12th power bits, or about 100 million pages of the Encyclopedia Britannica. And it's not just random stuff. Available cosmological models. A century ago, a century and a half ago, an atheist might very well have felt that the universe has always been here and stars perhaps have always burned, and yeah, we don't know how a star could keep going infinitely, but we don't know how stars keep going anyway, so no big deal. But with the discoveries of the nuclear processes, with the discovery of the expansion of the universe by Hubble, and actually a little earlier by his predecessor, it's become apparent that you're in an expanding universe that is running down in the sense that it's using up the hydrogen fuel and such available. The upshot of that was, by the end of World War II, two basic kind of models had arisen in scientific circles for cosmology. One of them was a model that the universe came into existence in some sense at a finite time in the past and has been expanding from that, a Big Bang model. And perhaps we should say a little something later about varieties under that. And the other model was, no, the universe has always existed. Is the perfect cosmological principle that things not only look the same in all directions, but they look the same at all times in the history of the universe. That in their model of the universe always had about the same density over large volumes. It always had a certain number of dying stars and a certain number of new stars and a certain number of new galaxies and old galaxies and that sort of thing. And they said, you know, this is really the scientific feature of methodological atheism or methodological naturalism spread out, you know, carried to full degree. And I think a number of people bought into that. However, a problem developed fairly early on, and that is, as they began to try and look further and further into the universe, researchers were trying to find out whether we lived in a universe that looked like it was getting thinner, less dense now than had been earlier, or whether the density looked like it stayed the same at all times in history, because the Big Bang predicted a hot, dense universe that was becoming thinner and cooler as it went on, whereas the steady state predicted